Good morning, everybody. Welcome to video number 4 of our equilibrium series. I hope you're doing great in our containment days. Today's a great day because you woke up alive. I think that every morning. I woke up. It's a good day, regardless of what's going on. But hey, we're going to make this a pretty simple lecture here. We're going to look at what this equilibrium constant means. What does its value signify? And then we're going to look at what that is at equilibrium versus not at equilibrium. So when we're starting some of these, we're going to have some pretty crazy mathematical problems involving equilibrium expressions later on down the road. And one of the first things we're going to want to do is look at, hey, are we even at equilibrium where we can apply the equilibrium expression? Or are we starting out at some conditions that are not equilibrium? And then this reaction is going to drive either towards products or towards reactants to achieve equilibrium, because that's the happy place for a reaction. It always wants to go to equilibrium. Think of that as kind of the bottom of a well, right? You're either here going this way, right? Got too many products, it's going to head back to reactants, or too many reactants, going to head down to products, but it's always going towards the bottom of that well, and that's the equilibrium condition it wants to go at. So first, let's look at the value of K and what does it mean when you look at it, because we're going to look at tons of tables in your appendix in the back of your book and other tables, and I've typed those all out for you, and they're on Canvas under handouts, so you can download those to your phone or print out hard copies if you want to. But the value of K, if we look at what K is real quick, right? That magnitude is going to tell us how far that reaction occurs. We looked at earlier, before all this chaos happened, there's 3 main things we're going to look at for a reaction, right? Does it actually occur? Thermodynamics is going to let us calculate that. If it does occur, how fast does it occur? That's kinetics, of course, which we covered in the last chapter. And then how far does that reaction go? And that's what equilibrium talks about, right? How many products do you have? Is it all products, part reactants, all reactants? That's what equilibrium tells us, especially for reversible reactions. So we're going to look at the magnitude of K and just look at mathematically, since K, the equilibrium constant, is the product concentrations raised to the power of the stoichiometric coefficient over the reactant concentrations raised to their stoichiometric coefficient. The bigger the value of K, the bigger your numerator, which means you have more products, right? The smaller the value of K, the smaller your numerator or bigger your denominator, and the more reactants you have. So we can just look, if you're given a value of K, or you look up in a table somewhere, you can pretty much tell whether you are product favored or product dominant, or reactant favored or reactant dominant. We use those terms. You heard product favored, reactant favored. So let's take a look. If our numerator is huge, right? We got a lot of products, not many reactants. We're going to have a value way bigger than 1. So if K is bigger than 1, we call that product favored. All right? You can just look at it mathematically. If you've got a smaller numerator and a larger denominator, or more of the reactants, right, we're going to have a K value less than 1. So we call that reactant favored. Reactant favored. So keep that in mind. It's a quick little thing that I look at when I look at a value of K. And we're going to look at this in terms of strength later on. If you've got really, really strong reactants, like strong acids and strong bases, we always say that that goes to completion. It's got incredibly high K values, right? If you've got strong oxidizing and reducing agents, it's going to drive towards the product side pretty high. Lots of products, very few reactants. So keep this in mind, and what we're going to do is now look at what if we're not at equilibrium, which way is a reaction going to go to achieve equilibrium. Hey guys, okay, so when we're looking at a chemical reaction, and we're not sure if it's at equilibrium or not, we're probably going to be given some initial starting concentrations or pressures, whether it's a Kc or a Kp. What we're going to do is calculate what's called a reaction quotient, all right? So this is going to allow us to predict which way a reaction is going to go to achieve equilibrium. Is it going to go from reactants to products, or is it going to go from products to reactants back towards the left? We don't know unless we actually can compare some numbers. All right? So what we're going to do is we're going to set up the equilibrium expression exactly like we did before. But instead of calling it K, we're going to call it Q. All right? Q is your reaction quotient. So think of it as the equilibrium expression, just not at equilibrium, all right? But it could be at equilibrium, we don't know. But what we're going to do is we're going to calculate this value of Q. We're going to compare it to K, right? We're going to compare Q to K. I'm going to erase this board and show you the results of that, right? If Q is bigger than K, if Q is equal to K, or if Q is less than K, that's going to tell us whether this reaction is going to drive towards products to the right or towards reactants to the left. It's going to be very useful for us. So let me erase this board. It's pretty simple to set it up and show you what happens if Q is bigger or less or equal to than K. Hey guys, okay. So now what we're going to do is theoretically look at Q versus K in predicting reaction direction. Then we'll do an example problem in this video and get into some juicy stuff later. I think I saw my son running around back there last time, so if you see little heads bobbing around, we're running our lecture hall at home here because we have to. So with 4 young kids at home, you never know what's going to happen. Cats and bearded dragons and birds everywhere. It's going to be fun, but hey, have fun whatever the situation is. That's my philosophy. So if we're stuck at home, let's have some fun with it, all right? So again, we've got some generic reversible reaction. We're going to test and see, hey, let's set up our reaction quotient given some numerical values of concentrations or pressure, depending if it's a Kc or a Kp. And then let's look and say, we have 3 scenarios, right? So either Q is going to be equal to K, Q is going to be less than K, or Q is going to be greater than K. There's really no other options for that. So what happens in those scenarios? So let me grab a pen here. If Q is equal to K, well, that must mean we're starting at equilibrium. That makes the problem a heck of a lot easier, all right? So if Q is equal to K, we are at equilibrium. But not every reaction you're going to be given for problems is going to be starting at equilibrium. So this is always a first step you'll do for every equilibrium problem. Hey, am I at equilibrium? Calculate Q. If Q equals K, I am. If it's not equal to K, I'm not. And then I got to figure out which way this baby's going to shift. And you're going to see how this pans out very importantly later on in some of these equilibrium calculations we're going to do. All right. Well, let's say Q's smaller than K. What does that mean? Well, Q wants to be K. The driving force is for Q to be K. So if Q is smaller than K, it wants to get bigger and it wants to become K. It's going to that reaction is going to shift so that Q gets larger until it equals K, and then we're at equilibrium. Hey, and then we have constant concentrations at that point. Well, if Q is too small, that means our numerator is too small, right on? Which means we don't have enough products because products are in the numerator. So that means the reaction is going to drive more towards the right, towards the product side, and build up the product concentrations, reduce the reactant concentrations, and that will drive Q up until it equals K. So we call that a driving force to the right-hand side. It will shift right towards products until Q is equal to K. Pretty straightforward. Now, I think the next scenario, Q greater than K, is going to be pretty obvious. It's going to be the opposite of that one. But I like you to think about it rather than just memorizing things. Think about what these numbers mean, right? So if you do a calculation and you take the initial conditions, concentrations or pressures, depending if it's Kc or Kp, and you get a value of Q that's greater than K. And again, K is a constant that you can look up in tables. It's usually provided for you, but I like to give tables. And I'll pull a table out and put it on. When we're doing actual problems, I'll show you the table that we're going to be using, which I provide for you on tests and quizzes. So if Q's too big, it wants to get smaller until it equals K. So if it's too big, it means the numerator's too big and I get too many products. So it's going to shift back to the left-hand side to have less products and more reactants, bringing Q lower and lower and lower until it equals K and we're at equilibrium, all right? So what happens if Q is greater than K? It's going to shift to the left. So that will shift left towards reactants, right? Pretty simple until Q equals K. And then we're at equilibrium and all the concentrations are constant, and then we can do our equilibrium calculations and problems that we're going to be doing. So pretty simple concept, Q versus K. So that reaction quotient will always be our first step in all the problems we're going to do, all right? So what we're going to do in the next video is take a look at specific types of equilibrium, right? For acids, bases, whole bunch of, solid solubilities, just as an introduction to future chapters. And then we're going to get into the thick of it. It's going to get crazy fun. All right, have fun, guys.